Good morning, everyone. My name is Anneli Strobel. I am the manager of EU-PolarNet 2, which is a Horizon 2020 coordination and support action coordinating the cluster. I will start a bit with the history of the cluster, which started as the EU Arctic cluster in 2016. And the background is that in April 2016, the Commission and the High Representative published an integrated European Union policy for the Arctic, which was outlining the European Union's interest in playing a key role in the region. The three priority areas that were stated in this policy was first, climate change and safeguarding the Arctic environment. Second, sustainable development in the Arctic. And third, international cooperation on Arctic issues. With this policy, the EU stated its intent to function as a major funder of Arctic research, which was also reflected in this quote from Andrea Tilche from the Commission, who said, spending in Arctic research and observations is not a cost, but an investment that generates benefit. So the 8 EU Arctic projects that were existing in 2016 took the initiative to join forces and launch the EU Arctic cluster. Here on the right, you see these first 8 projects of the Arctic cluster, with EU-PolarNet being one of them. And then in 2019, the cluster changed its scope and became the EU Polar Cluster, also including Arctic and Antarctic projects, and now covering both poles. Okay, here we are. Currently, the cluster has 21 active projects and 2 partners, the EPP and SIOS, and together we call all of them the cluster members. We have 6 polar projects, 16 working in the Arctic and 3 in the Antarctic. Some of these projects have already ended, but they remain members of the cluster for up to 2 years after their official end date. That is why you see a bit more projects listed here than the ones that are actually still running. The cluster is currently organized around different task groups. We have 5 of them. The one is focusing on communication and dissemination, which is led by my colleague Elena from BAS. Then we have a task group about stakeholder engagement led by Annette Schiepska from the Netherlands. Then we have the data management task group led by Stein and Stein. Then we have an education task group led by Apex. And Katharina from Lund University, and we have a task group on policy advice led by Nicole Bibo from EU-PolarNet and Gustav Siegmann. The reason or the background for the cluster why we are working together is because we are creating synergies between already planned activities to maximize the impact and the visibility of European polar research. This is also pooling the resources, financial, in-kind, human resources, and to finally upscale the efforts. We are also increasing our knowledge sharing and maintaining the legacy of finished projects. And we have joint activities related to communication, stakeholder engagement, data management, education, and policy advice that were reflected in these task groups that I showed before. In 2022, EU-PolarNet 2 has taken over the mandate to coordinate the EU Polar Cluster. We have in our project 2 dedicated tasks related to this coordination. The first task is led by Elena Ford from BAS and Renuka Bade from the EPB. And this includes setting up annual cluster meetings. One we had in 2020 at the EU Polar Science Week that was online. The next one is planned for June, so in 2 weeks in Brussels, our first in-person meeting since the pandemic. Then we also set up one for 23. And among our tasks was also to define the vision and the mission of the EU Polar Cluster, since this was not existing before. So we defined some terms of reference that are in force since October 21, and you can find them at the website, but I will also come back to them soon. And we also have another task in EU-PolarNet led by the University of Lisbon, who is supporting the cluster in communicating and advertising all the cluster activities, engaging the partners in the cluster, and promoting EU-PolarNet through the cluster projects and the institutes. Okay. As said, one of our tasks in EU-PolarNet was to define the vision and the mission of the cluster. And as part of these terms of reference, which we have developed together with all cluster members last year, the vision of the cluster was defined to be a strong, well-connected ecosystem of European polar projects and organizations operating together to substantially increase their combined impact and legacy. The mission that we defined in the terms of reference is to connect EU polar cluster members to further develop European polar research, observation and infrastructure and modeling community network. Also to organize joint activities by cluster members for greater impact than possible individually, while minimizing duplication, sharing workload and avoiding stakeholder fatigue. We also support the accessibility of large-scale EU-funded polar projects. And the legacy outputs after their official end, and also to share advice and best practices among EU polar cluster members, also to promote the European polar research community, and importantly, to provide a single contact point to all EU polar cluster members for external partners. Now coming to some examples of the joint activities that we organized or are going to organize with our cluster members. For example, we had joint booth at the Arctic Circle before, and then a video slideshow at the Arctic Forum last year. And we are also preparing a joint cluster booth at the SMM in September this year, which is a big fair for maritime industry, where you can finally meet our new projects at us in person again after a long break. And we also have these annual meetings, set one at the EU Polar Science Week in 2020 and the upcoming one in 2 weeks in Brussels, where we finally meet all projects. And then we are also organizing thematic workshops on different topics, like the impact of COVID-19 on the individual cluster projects, or the impacts of the current Russia developments on the projects. Then other activities, for example, that we organize joint policy advice events, such as a webinar about the new Arctic policy and research and innovation, which was organized by EU-PolarNet, EPB, and the cluster. And we had representatives from Just North, Ecotip, and Nunatayuk speaking, and also very high-level representatives from the Commission to promote the new Arctic policy, which is a very valuable document, and I can recommend to read it. We also had a cluster side event at the COP26 pavilion last year called Polar Warming, Global Warning, jointly organized by PolarNet, EU Polar Board, SOCIC, Arctic Passion, and Protect. We also provide a lot of collaborative tools for our members to foster communication and exchange between us, and to inform our stakeholders. For example, we are active on Twitter, on Facebook and LinkedIn, where you can follow us. We also have a website, polarcluster.eu, and if you scroll down a bit on the first page, you will find a link to sign up to our news mailing list, where you can receive our regular newsletters with latest news for projects and upcoming events. As already said, the cluster works also together to increase its impact. by organizing collaborative events or workshops. And to organize this, we share our information among the members and to our audience on our website. And there we have Google Calendars, where you can find collaborative events or also events of the individual members and sessions. And we also take the opportunity or offer to publicize open calls or job vacancies or similar things from our members. For example, open calls for transnational access from our project Arise, calls for seed money from EU-PolarNet to job vacancies, calls to submit publications, etc., etc. So it's worth having a look at this this web page where you can find all these nice opportunities. One of our thematically common and overarching goal of several cluster members is to build and operationalize integrated Arctic observing systems, promoting community-based observation and best practices in Arctic observation. And through this overarching goal, the cluster members aim to address a wide range of scientific challenges in the Arctic. One of them is to contribute to climate change observation and environmental challenges. Some of our projects or members are investigating, for example, processes affecting the Arctic climate change and its impact on weather and climate of the Northern Hemisphere. We are also assessing the status of ice sheets and glaciers, the effects on future sea level, and predicting changes in the cryosphere. Projects are also assessing the developing and maintenance of a dynamic observing system of the Arctic Earth system. And we are also improving data collection and dissemination to support climate research. We actually have 5 cluster members grouped around this topic of Arctic observation. We have INTAROS, who aims to develop an integrated Arctic observing system for the atmosphere, ocean, cryosphere, terrestrial sciences, and local communities, with focus on the in situ component of the observing systems, also including data management. Then we have Arctic Passion, which aims to co-create and implement a coherent integrated Arctic observing system, the Pan-Arctic Observing System of Systems, Pan-AOSS. And then we have another member, KEPLER, that is already added, who aims to provide a clear, concise, and achievable roadmap for Copernicus to evolve its Sentinel monitoring program. You should hear about it later. Then we have iCube, whose objective is to synthesize data from comprehensive long-term measurements, intensive campaigns, and satellites collected during the project or provided by an ongoing international initiatives. And last but not least, we have, of course, our member SIOS, studying the environment and climate in and around Svalbard to develop an efficient observing system and share technology, experience, and data. The added values that the Polar Cluster receives through all these collaborations and joint activities and the joining forces in its thematic activities are higher impacts than single projects outputs, upscaling collective projects efforts, we increase our knowledge sharing, we have less but better engagement with stakeholders, a greater visibility of our projects and outcomes, and of course a better use of the citizens' money. With that, I would like to thank you a lot for your attention. I'm sorry. And if you have any questions, please feel free to contact me by email or our cluster coordinator, Elena. You will find her email or contact at our website. Thanks a lot.
So yeah, I will present the KEPLER project output. Well, that was finished already last year. I will present in particular the work package 3, which I was in charge. I am Carolina Gabarro from the Institute of Marine Science in Barcelona. And this work package was to identify the research and capacity gaps related with the remote sensing part for observing the polar regions. This is the project, was a space topic, was a coordination and support action, and take 2.5 years. We were 15 partners. It was led by Metno, Nick Hatch. Just a brief explanation of what was the objective. The objective was very focused to think and try to provide or recommend to develop a new roadmap for improving the Copernicus system, providing data, but especially with focus on Arctic or sea ice and polar environment conditions. The idea was to put a step beyond to the Copernicus system for the next phase of Copernicus, and it was very important also to understand what was the user's needs, because what it is required is to increase the number of users for Copernicus. It was divided in different themes. First, how to raise awareness of the Copernicus program, engaging more users, and improving at the end, improving the sea ice mapping and forecasting. So now I'm focusing, this the project was divided in 6 work packages, as you can see here, and management the 7th. And I will present the work in work package 3, which was research and capacity gaps. The first task of this work package was 4 tasks, contained 4 tasks. The first one was focused on analysis on the situation of the in situ data in Copernicus, and they did some recommendations. This is very short. They said that it was important that the Copernicus service could make greater effort to highlight and promote the citizen science projects, which there are some, but not really promoted by Copernicus. And well, we said that it could be a good point to manage to have much more in situ measurements, which at the end was also important point to notice, which was important to prioritize the collection of in situ measurements, especially for the K value remote sensing data. Task 3.2 was to analyze the situation of new in situ sensors like airborne, so new techniques. So there are several techniques and systems were analyzed, as you can see here, a manned aircraft system, hubs, drones, balloons. They conclude that there are some promising results, even though some more development is required. And it's very important that these sensors or these techniques can be lower cost, have lower cost, or being cost effective, because otherwise it's difficult to pay for something which is not shown that is going to be very good. So the idea was to promote to Copernicus, we will propose to Copernicus to monitor this development and promote somehow the use of these new techniques. Now I'm going to talk about task 3, which is the main core of this work package. That was more, it was based on the identify the gaps on space-based monitoring, which is being served in Copernicus. The first thing we did was to do a list noting all the remote sensing parameters which are currently being observed with remote sensing data, and which of those were offered in Copernicus. And we identified 15 products which are being served in universities, research centers, whatever, but are not included in Copernicus. So this is the list of parameters which are not being currently offered to Copernicus, and the recommendation with it was to distribute these 15 remote sensing parameters which are being tested and with good quality, because there are some papers already published and which could be served. Then we analyzed also the future Copernicus Sentinel mission, which was called before HPCM missions. which that was had the prior objective on polar observations. Those Sentinel expansion missions are SIMA, which is a multi-frequency radiometer going from L1 to 37, from 1.4 to 737 gigahertz. We also analyzed the Crystal mission, which is a QUKA altimeter, combining both frequencies. And also we analyzed Roselle mission, which is an L1 SAR. So you can see here, we found these parameters as a priority parameters, which was identified by the PEC for polar monitoring. And we analyzed which of these three missions could provide the identified priority parameters. And you can see here the color blue, blue is SIMA, green is Crystal, and red is Roselle. So we identified in reality that we need all of them to cover the parameter list, which was identified, which that was important to provide. So the recommendation is evident that we would like to have the three missions flying, and if it can be in tandem would be better, because then we can use and compare the results between them. Then we also analyzed the potential synergies, which we considered that was not being done in Copernicus. We evaluated the current and the potential synergies using different satellites to provide certain parameters, which we consider combining satellites, the quality can be improved, the resolution can be increased or improved also. So you can see this table talking or putting on the top row the different sensors or type of sensor omissions. You can see it here, and all these synergies are already tested experimentally. The ones that are cited here in the report, which is a very extensive report, we put the reference. The green boxes are synergies for land applications, and the gray for sea and ice applications. The red are the ones that are being currently in operation and in offered in Copernicus. So you can see that only 3 of these synergies which are being published are being served in Copernicus. And in bold, we wanted to note and make awareness that the bold are the ones which could have an important impact to end users, intermediate and end users. So you can see that there are many parameters. I think that we found 18 potential synergies of different types of sensors, which could improve the resolution or the accuracy of the parameters. And only from these 18, only 4 are currently in operation in the current phase 1 of Copernicus. So the recommendation was clearly to promote the production and distribution of these potential synergies between sensors, since we have a lot of measurements and we should find how to combine the measurements to improve the accuracy. We also assess the data simulation system, which is being done or utilizing the models in Copernicus. They found that several observations are routinely assimilated. However, some present several limitations, as temperature from infrared, sea ice thickness, ice drift, chlorophyll. These ones need to be improved in the models, and some have some medium limitations, which is a sea ice concentration. Also, we found that several parameters are not being assimilated, and we recommend to do that. One is salinity, which this was all now the Topaz output model system do assimilate the salinity from SMOS, which is very new. And also we recommend to assimilate the wave height, which I think in this new version of Topaz 4B, they do also the simulation of salinity and wave height, but this is very recently. We also proposed to analyze if it would be possible to assimilate data at lower processing levels, not maps, but maybe path, which has some advantages, and all this is described in the report. So recommendation is clear. Also, we did some tables to highlight where were the gaps for polar monitoring. And here is very short report. You can go to the report, which has like 200 pages, but there are some some parts of the report with a summary. What is in general is we need to increase the in situ observation, reduce the polar hole, and it was also important to reduce the timeline between observations and data arriving to the end user, so reducing the data flow timeline. For land monitoring, it's needed to improve the snow cover, snow avalanche, snow water equivalent measurements, among others. For sea ice monitoring, snow depth on sea ice is a clear problem which hope Crystal can assess. We need near real-time high-resolution ice analysis. For shipping, it was required for shipping, also improve the sea ice concentration forecasting. And also we have a problem in summer, which the sea ice concentration and ice thickness has limited accuracy. So these are points which some focus should be put to improve the polar monitoring. The last task of this work package was to try to find a way on how the assimilation of some parameters could impact severely to the results of the models. Okay, for that they used a method which called quantitative network design approach, which presenting or setting some observational scenarios, they can evaluate the impact of using one parameter on another on the assimilation of some data, both in situ and remote sensing. The conclusions were these ones I'm going to present. They put two scenarios. The first one was in a scenario of the Arctic sea ice ocean. And they found that using Sentinel-3, rather freeboard, the output is much better than using Cryosat-2 because of the higher coverage. So they found that this brings important a step forward on the output of the models. They also found that it was better to use the freeboard, the raw freeboard product, than using the derived sea ice thickness product. And they also found that using the simmer-like sea surface temperature produced better outputs than using the infrared sea surface temperature. On the second scenario was in a scenario of atmospheric CO2 to constrain line-based fossil fuel CO emissions. And they found that an increase of number of sites, in situ sites, providing continuous in situ CO2 samples benefits much more than using sensors with higher accuracy. And also they found that combining in situ measurements with a single CO2M satellite map provides much better constraints for deriving the CO2 emissions outputs. So the recommendation was that the quantitative network design is a very good approach and is ideally to suit and support the planning of future missions. It should play a predominant role in the mission design. That's clear, because with this we can really assess which parameters can bring a step, important step on our knowledge and monitoring of the polar regions. We also provide some suggestions. The suggestions I have commented before. We decided to order in time frame. The immediate actions would be to improve the communications between the stakeholders and end users, which is essential. We also immediately consider that Copernicus should promise the citizen science to enhance and increase the number of in situ data. we call opportunities. These are things that could be done in a period of between 1 and 5 years. This is difficult to put this range, but well, we consider between 1 and 5 could be done if Horizon 2020 or Copernicus considers it's important. For example, prioritizing in situ measurements, as already said, ensuring near real time, if it's possible, for critical operations in the Arctic, distributing the parameters which are not being currently distributed in the Copernicus, as already shown in the table, promote the synergy between different sensors, promote the research on synergies, which is required also, advancing on the simulation of new data satellite. And here are some challenges in a further period of time between 5 and 15. We said that, well, we promote the HPCM or the next Sentinel generation satellites, as already explained. We said it's important to improve the data communications with satellite in that region, which is limited and very expensive, and some other recommendations. And that's all. I think time has gone. If you have any questions, you can contact me here, and you can find the final report in this webpage. We have also a report of 5-6 pages, which is a summary of all the long report. If you're interested, you can go to all those documentation.
I would like to present some results from INTAROS. This project has now been completed. All former deliverables have been submitted to the Commission. So now we are in the just the last review phase of the project. First of all, this is a project which is dealing mainly with in situ observing systems. So the objective has been to develop, improve, and extend these systems for the atmosphere, ocean, cryosphere, and also terrestrial sciences, as well as including local community observation. So the project have involved more than 300 scientists from 49 organizations in 20 countries over a period of 5 years. So the focus has been to conduct field experiments in different parts of the region. This map shows the locations where the project had been working. All the green boxes refer to terrestrial sites, and the blue boxes refer to observing taken in the ocean or on sea ice in the circumpolar region. So, of course, this was, let's say, affected quite severely by the COVID pandemic, starting in 2020. But many of those systems, they started work in 2017. So we had 2-3 years, quite well organized, I would say, and results were quite encouraging. We got a lot of data, but of course, when the pandemic started, many of these field experiments had to be either canceled or postponed or reduced. So, but the overall conclusion is that we got reasonable good, let's say, data collection in all the thematic areas. And I will show some examples of that now. For the oceanography work, we had moorings north of Svalbard. This example here shows time series of ocean temperature in the upper 800 meter taken from a McLean profiler over a period of 3 years. And what we see here is just the core of Atlantic water flowing into the Arctic basin just north of Svalbard, as you see on the map. And this work was led by Agnieszka Besinska-Müller from IOPAN, together with colleagues from Lucerne and from Institute of Marine Research and others. And another example is the snow ice mass balance work, which were done using a number of these buoys. They were used, the so-called Simba buoys, which have been developed at SAMS and have now been used by many other institutes. Here we see an example of to the left, a map of a cluster of buoys which have been deployed over the period from 2018 to 2020. And in the middle, we see example of a time series of temperature measurements showing the cooling of the snow and the ice, which also can be used to infer snow thickness on top of the ice and the ice thickness. And with a number of these measurements being obtained, you are able to follow the seasonal changes in the ice thickness and also the snow cover on top of it. So this work was led by Bin Cheng from FMI. And for the ocean work, we were working together with the AVIPEV laboratory in Ny-Ålesund. The example we see here is a time series of CO2 measurements in Kongsfjorden near Ny-Ålesund. And the time series here shows the CO2, partial pressure of CO2 in seawater over a period of 6 years from 2015 to 2021. This is the case where data collection were interrupted because in the pandemic situation, the people couldn't just travel. They were not allowed to travel to Ny-Ålesund. So the system could not be maintained. So it had to be canceled. I hope they are able to restart it again now. In Greenland, in the Greenland coastal waters, there has been extensive collaboration between different institutions working with sea ice modeling, hydrodynamic modeling, ecosystem models, and also using data from the Greenland ice sheet, the discharge data from the Greenland ice sheet. They use satellite data of sea ice and also in situ data from ship-based observation. And this has been put together in an integrated study of the ecosystem in this area. That is work led by Aarhus University in Denmark. Then another example is the work with sea level and land rise, because there is a network of tide gauges around the circumpolar Arctic, which have been measuring sea level for a number of years. And we know that sea level is one of the large climate issues, and satellite altimetry are used extensively. But here we have focused on the use of tide gauge data. And the issue is that since you have land rise in some places, and this affects the measurements or the estimates of sea level rise, we see two examples of time series of sea level change from tide gauges, which are the blue line in these two plots. And when you correct for the sea level or for the land rise using a so-called VLM model, then you end up with another estimate, which is then the absolute sea level rise. So this is work carried out by Danish Technical University. It's Karsten Ludvigsen have been the PI for this work. On the Greenland ice sheet, we have had extensive efforts by GEUS, led by Andreas Ahlström. They have been working with operating a number of automatic weather stations, which have a number of different instruments. So the project have contributed to increase the number of instruments. And to the right, we see an example of a snow water equivalent data set from the new SnowFox instrument, which are contributing to improved measurements of these crucial parameters. There are also a number of other measurements. For example, the ice drift from satellites SAR has been included, and also the estimation of the discharge going from the glacier into the ocean. Going on with more terrestrial work, this is an example from the Canadian Arctic, where we have been working with University of Laval. They are doing in situ measurements in different Canadian stations to measure the permafrost, the measure including the snow depth and other various parameters like CO2 and CH4, which are released from the permafrost. So this is an example of a time series of snow and soil temperature measurements in one of the sites. I mentioned that the community-based observation is an important part here. And this example here is taken from Greenland. The thing is that there are local community who have developed a network of observations that they register in a so-called community-based observing system. It's in principle a very simple thing. You observe a number of various parameters. You observe marine mammals, fish, birds. You can measure sea ice variables and some other climate variables. And this is registered in a certain system. And when you do this over time, you accumulate valuable information, which is not captured by standard scientific methods. So this example here shows work which is now organized in a network in Greenland, which is called PISUNA. So this network is led by, or the work in this project is led by Finn Danielsen from Nørbeko in Denmark. Geohazard is another issue in the Arctic, and we have had people working with different problems here. This case here is about seismology, observing earthquakes, and up to now, almost all the earthquake observations are made from land stations. There are very little ocean-based observations, and a large part of the Arctic is ocean. And as you see on the left map, there is basically a lot of earthquakes along this ridge in going through the Atlantic Ocean, the Arctic Ocean. And in this project, we put out these ocean bottom seismometers. We see the picture to the lower left. So with this instrument, you can register earthquakes in the deep ocean, and there were done experiments with that, which help the seismologists to get better understanding of the location of earthquakes, in this case, between Greenland and Svalbard. We also tried some citizen science seismometers, where people could install small, simple devices in their house, and that could be registered in, as we see to the right. And this is a helpful thing which can add more data to seismology network, which is, for example, in Greenland, there are very few such observations. A little bit about the data value chain. I see time is running quickly. Just about the data value chain, because it is very important that how do you make sure that the data are processed, archived, disseminated, and used by different user groups. And the flow here shows the different issues that we are facing, because a lot of the issues are related to how well are data archived in data repositories, how accessible are the data, how are they used in different applications. So we have worked with, to the right side here, we have example of activities like developing cloud platforms or testing cloud platforms. We have a portal where all the activities in the project are reported. We have a specific data catalog. I will show example of that. And then there is a number of stakeholder applications where we see how data are used. This is example of how you look at the data flow from observation system to the left, going through the different steps, ending up with services which are beneficial for the society in various ways. This is example of how you do it for snow avalanche warning. Yeah, this is the portal for INTAROS, where you can go to different subsystems here. We have the data catalog, we have an ArcMap survey system, and other projects and services that we have developed in the project. So I recommend, if you're interested to look more into this, please go to this website and go to one of these sites. INTAROS catalog is something we want to highlight because there were extensive efforts to register data in the catalog, and these data are residing in a number of different repositories. So it is like a metadata system which help people to find the data which have been collected not only by INTAROS but also from from other collaborating projects. This is the ArcMap. It's an inventory of in situ observing systems. So in the beginning of the project, we had to get some idea, you know, who is doing what and where, because there is a number of different systems, but it's very difficult to get a good overview. It's difficult to know who is doing what and so on. So we set up this ArcMap survey system, which help us to get idea of where our observing system located. And here we get some statistics out of this survey showing which countries are contributing, how are the funding distributed, who are funding these activities, and so on. So this is a system which we will continue to operate, and it can be updated. We encourage people who are interested in the in situ systems to use the system. It helps to find out who is doing what and where, and because there is more and more activities there, and it's useful to know where things are going on and who are doing it. And finally, we produce this roadmap. It is a plan for what should be done to improve and sustain the observing capacity in the Arctic. And again, this is focused on the in situ component. So we pointed out three main conclusions. First, and this is of course very general because it applies for all the scientific areas, all the disciplines. We need to strengthen collaboration between the countries, programs, and institutions who are involved in planning and implementing the system. And that's because in Copernicus, all the in situ components, they are delegated to the national initiative, to the national program. So we depend on increased collaboration here in order to really develop an integrating Arctic observing system. I mentioned this streamlining of the data delivery change, going all the way from sensors to the users. And this is an effort which needs, again, collaboration between the scientists producing the data, also technology experts who can set up these delivery chains, and also the service providers who can say, how do they want the data? How should the data be delivered, and so on. And finally, and this is perhaps one of the major challenges now, but also major opportunities, how do we adapt the observing systems to evolving technologies, which regards sensors, platforms, data transmissions, which include or will include an Arctic broadband system, and also more and more digital methods will help us to process and manage the growing amount of data. And with that, I end my presentation. Thank you for attending.
Arctic Passion, okay, this talk is going to be somewhat aspirational in nature because Arctic Passion hasn't been going that long. So really I'm going to present some of the goals and ambitions of the project rather than anything we've actually achieved. But it very much builds on the excellent foundational work that was undertaken in INTAROS and that Stein just described, and in particular, attempts to address that last bullet point that he had in his presentation on new technologies and different types of data observing system. But it also builds on INTAROS in the sense that there is a stronger focus, or there is a stronger focus in this project on satellite observing systems, and in particular the Sentinel satellites and the Copernicus services. And that was something that the Commission was very keen to see. I'm presenting this on behalf of various different groups who are working on different satellite or Earth observation components within the project, including Gorm from Danish Met Institute, Anna from RV, and Kasika from Finnish Environmental Institute. And I thought I would let me just get this working. I thought I would just start with a brief introduction to the project because most of the people here probably don't know too much about it. This is pretty much a carbon copy of, if you like, the mission statement for the project, taken from one of the documents that was submitted. And basically, we want to develop you can read it. I'm not going to repeat everything there, but the overarching goal is to produce an integrated, coherent observing system for the Arctic, a kind of observing system of systems, in effect, for Pan-Arctic. And of course, that includes much more than the cryosphere. So we have components. In fact, we have, I think, 7 pilot services that we're developing within one of the work packages. And some of those are related to marine acoustic pollution, atmospheric pollution, many different parts of the Arctic environment, in addition to cryosphere, but I'm going to focus mainly on Earth observation related to ice. It's quite a big project, for currently 43 partners from 17 countries, 50 million euro budget over 4 years. And a key thing to note is that we're just under a year into the project. And because this started during COVID, we haven't actually met as a consortium yet. And the first general assembly of the project actually takes place in about 2 and a bit weeks' time, just outside of Copenhagen. So still very much in the early days of developing the program. A little bit about the different components of the project. There's actually 10 work packages. The last one is not so relevant, and so I'm focusing on the 3 key pillars here. Let me use laser pointer. And the one that's most relevant to the workshop today is pillar A, which is the observations and services. And in fact, I think the main areas or the main work packages which are using Earth observation data will be work package 1, where we're establishing some of the approaches that we want to use and developing some of the what are called Arctic climate variables and shared Arctic variables. So that's ACVs and SAVs that are going to be developed within the program over the 4 years. And work package 3, where we're doing this QND analysis that Carolina mentioned related to KEPLER, looking at the robustness of the different observing systems and their dependency on certain data sets or observations. Okay, and yeah, this is quite an important point. So you're probably familiar with concept of ECVs, environmental climate variables. Sorry, essential climate variables, developed between WMO and ESA primarily. Within Arctic Passion, we're building on that concept and taking those core climate variables and sort of translating them to services rather than products that are relevant to the Arctic. So we've defined something called ACVs, and shared Arctic variables are ones where there's a significant component from user community in terms of defining the service that is provided. And it's very important that the aim of the project is to develop services, not products. And there's a big difference between those two. And this is just to show that, of course, in addition to the satellite observations, we're also involved in a number of field observations. Obviously, the ones in Russia are sort of, major question mark over whether those take place. But this map was taken from a nice interactive portal that is on the Arctic Passion website, developed by Arundel. And shows some of the sites where we're undertaking in situ observations as part of the overall program. And you can see on the right some of the, well, they're acronyms, but down here we have different types of pilot services. So PS4 is, I think, wildfires and aerosol pollutants, acoustic marine pollution, lake ice, and so on and so on. So that is a really brief overview of aims and objectives of the project. Just to say, now go on to some of the key activities at the University of Bristol. We are responsible here for the land ice services or the land ice variables that are going to be developed within Arctic Passion. And one of the key ones that we're currently developing is not just an Earth observation product. It relies heavily on Copernicus products and in particular high-resolution topographic data sets for the whole of the Arctic. But the goal here is to produce operational runoff estimates for all land ice across the Arctic. So it's not just Greenland, obviously, it's the Canadian Arctic, Russian Arctic, everywhere, at high spatial and temporal resolutions. So the goal here is to produce daily runoff estimates at the margins of the glacier, obviously. Second key activity in Bristol is to develop an operational service that is both carving front locations and related to that iceberg carving fluxes. So for the fluxes, we not only need the carving front, but we also need ice thickness, which will be from a combination of freeboard and bathymetric data where we have it, or estimates of ice thickness from hydrostatic equilibrium where we don't. And this image on the left is actually part of the ESA, what's called CCI stands for Climate Change Initiative. I'm sure you all know what that is. And ESA have been developing a carving front ECV, essential climate variable, but just for 3 sites in Greenland. It's really a demonstrator rather than an operational service. And so we're not reproducing what the ESA CCI does. Here we're complementing, building on some of the methodologies that developed in the CCI, but doing it across the Arctic and providing something that's operational and robust in the sense that it's not solely dependent on just Sentinel-2, for example. One of the goals, and this is kind of very much something that's evolving, is to provide a historical record of changing carbon front locations across the Arctic, and how long that is and with what temporal resolution is still something that we're working on. It obviously it depends on the input data sets that we've got. Work being undertaken at DMI relates to what I've just described in Bristol. So DMI over some years have been working on both sea surface temperature data and land surface temperature data using infrared radiometry, and they have developed a ice sheet surface temperature product, which they're going to produce as a level 4 product as a time series, monthly time series over Greenland. And coincidentally, not so relevant to Arctic Passion, but basically the technology and the data are identical. They're also producing this for Antarctica. In addition, and again, complementing what we're doing in Bristol, which is sort of, if you like, ends at the ice sheet margin, where we do produce calving fluxes, but we don't track where those icebergs end up. That's something that DMI will be picking up using Sentinel-1 SAR data, so tracking iceberg trajectories around the margins of Greenland as an operational product as well. And of course, there's also a lot of work being undertaken there on sea ice concentration, sea ice extent, and also sea ice drift, using a range of different data sets, including SAR data, sea surface temperatures from infrared radiometry, and also producing a multiple decade, up to 4 decade time series of some of these products, in particular sea surface and ice surface temperatures across the Arctic. So they're also turning those products into, if you like, climate indicators. And this is just So this is very much a kind of even higher level product, which is an indicator of changing Arctic climate variables, more for less perhaps for kind of scientific applications and more for I don't know, wider use, but some examples there. So those are the key Earth observation activities related to land ice and sea ice. There's also a significant component looking at permafrost across the Arctic that's being led by Alfred Wegener Institute. And this is just to illustrate some of the products and parameters that are going to be monitored, again, using predominantly Sentinel data, but to extend the time series also Landsat. So on the left, we've got surface elevation, records of changes in that surface elevation, slumps and fire events, and changes in lake cover. And so these 4 panels on the right are all different measures of changing lake cover across the Arctic derived from satellite data sets. And this is just an example of the kind of service that is being developed at RV and that they've been working on currently. And it shows a lake drainage event and the potential kind of environmental hazard associated with that. So as well as looking at, if you like, climate variables, it's also hazard detection as well as part of that activity. And then the Finnish Environment Institute has a component of Work Package 1 where they're looking at lake ice characteristics from multiple different satellite data sets and existing Copernicus lake services, or sorry, products. And so the goal here is to turn some of these products into operational services that have a direct applicability to, I don't know, human activity and, you know, the various bullets shown on the left here. And this is an example of the use of some Copernicus products for lake ice monitoring that are being developed at FEI. You'll see in this particular example, partly to extend the time series, but also because this is a pan-Arctic product, so it covers a very large area. It's done this is being provided at relatively coarse resolution using MODIS data, which takes us back to 2000. So we'll have potentially a multi-decade time series of changes in lake ice characteristics. And that will be extended with even coarser resolution Copernicus data from the Sentinel-3. This SL-STR is a sort of advanced version of the long track scanning radiometer that's been on board previous ESA satellites, and it's a thermal infrared radiometer, so relatively coarse resolution, but quite good for looking at lake ice properties. And this is the kind of product that potentially you can get from those data, which shows changes in lake ice numbers. So I think I'm just about at the end of my time. It's, as mentioned at the beginning, it's a 4-year project. Haven't got an awful lot in terms of results at this stage, and the goal is to focus on services rather than products, and therefore we want these to be operational. Very much building on the foundation that INTAROS project started. And if you want to find out a little bit more about the project, this is the website here. You can send me, you can email me questions if you want, but for some of those, some of the activities, obviously, I'm just a kind of conduit for what the other groups are working on. And that's all I wanted to say, I think. My time is up.
Okay, yeah, so I'll just be talking about the SIOS Remote Sensing Working Group activities, and I'll be presenting this on behalf of, well, a range of people in SIOS, predominantly Sridhar, who is the Remote Sensing Officer, and he put together all these slides, so thank you to him for that. And if you've made it to this webinar, then I'm sure you know who SIOS are and what we do, but just to kind of give you a brief overview, SIOS is the Svalbard Integrated Arctic Earth Observing System. And the big vision of SIOS is to be the leading long-term observing system in the Arctic to serve Earth system science and society. I guess the mission kind of comes under 4 key kind of aims. It's an international partnership of researchers studying the environment and climate in Svalbard, but SIOS really wants to develop an efficient observing system, want to share technology, experience and data, close knowledge gaps in Earth system science, and also to decrease the environmental footprint of science. And that's kind of where the Remote Sensing Working Group really comes in. In terms of the consortium, SIOS currently has 28 institutions from 10 countries. So you can see some of the people in the bottom left there. And Earth system science really covers a range of various spheres: geosphere, cryosphere, atmosphere, hydrosphere, biosphere, but we also look at interactions with society as well. And kind of just to finish on the introduction to SIOS, what is it SIOS actually works towards? So it integrates new and existing infrastructure and data sets that are created around the Svalbard archipelago. It develops a network of systematic observations, and really key is building a long-term observing system. So long-term monitoring is really one of the big aims of SIOS. Sorry, just 2 seconds. We want to build better temporal and spatial coverage of some kind of the key observational data sets. And where the Remote Sensing Working Group starts to come in is that we want to integrate space-based and in-situ observations to try and answer some of these Earth system science questions. Okay, so the Remote Sensing Service, which is one of the main key strands of SIOS, we are a single point of contact for satellite information in Svalbard. We deliver information about opportunities on how to use satellite data. We streamline access to Copernicus program data, satellite data over Svalbard. We work together with various users and providers to improve the usability of satellite data. And what we're really working on right now is to provide tools for satellite data users and try and generate geospatial products through our activities, but also by working with other people working across the archipelago. And in terms of the Remote Sensing Working Group, we have 25 members currently from 15 SIOS member institutions. And we also have 2 early career scientists observers. So I am one of those early career scientists. I've been working in SIOS for 2 years, but been involved in the last 3 years. So it's a very good network of people with various interests in Svalbard science, but really interested in the remote sensing side of things. Okay, so thinking about some of the activities that we're working on, then one of the key things that SIOS, the RSWG is trying to work with is to facilitate the integration of satellite data and cal-val measurements, so calibration and validation. So we work with field scientists who come to Svalbard to obtain field measurements and facilitate work that can help with calibration and validation of satellite data sets and satellite data products. And that's kind of one of the really important parts of Svalbard, is that we're a relatively easy location to get to, and therefore we're a good location for conducting cal-val measurements. I guess one of the big successes of SIOS in recent years is the airborne remote sensing campaigns. So over the last couple of years, we've put out various calls for for scientists to use the Dornier airborne the Dornier airborne sense aeroplane, which is currently equipped with an RGB camera and hyperspectral imager. And through for the Dornier aircraft, we can generate high-resolution georeferenced images and build digital elevation models for various applications. And over the last 2 years, it's been really important because of the COVID pandemic to be able to offer scientists who can't get to Svalbard the opportunity to access and generate data that they need for their research. So in 2020, when we were kind of in the midst of the pandemic, we had 10 projects with 25 flight hours, as you can see some of the flight tracks on the left-hand side. And in 2020, we had a similar amount of flight hours with 11 projects. And this data will be made available through the SIOS data access point for the community to access relatively soon. Maybe Sridhar can update on that at the end. We also think it's really important to train people on how to use remote sensing data. And over the last 5 years, so since 2017, we've put on a variety of training courses aimed at various areas of remote sensing, ranging from marine and terrestrial to kind of more specific remote sensing training in hyperspectral, which was the training course that we had last year. And we use these training courses not only to train people, so we had 35 participants in our training course last year with 15 teachers. We use these training courses to work on data that we've gathered. So in this particular training course, we worked on the hyperspectral data that we collected on the Dornier aircrafts and try and learn ways in which we can process and analyze these data sets and work out what we can do with it to kind of answer some of these system science questions. And we're just preparing a manuscript on that. And Sridhar, I promise you to get you my comments over as soon as I can. This year, we're working on, I guess, what is really the big topic in not just geoscience, in various areas of science, which is artificial intelligence. And in September, this is all going to hopefully go ahead in person. We'll be running this AI for Svalbard course, and we're currently in the process of organizing this. And this is going to be, again, another really important chance for us to apply AI techniques and machine learning to SIOS data, again, just improving the usability and the applications of SIOS data for Svalbard science. So you're here on a webinar series, and we've been conducting these webinar series ever since the pandemic kind of took hold in 2020 as a way of bringing people together from around the world so that we can continue to build the SIOS community. And in 2020, this was really important, and it kind of provided an experience for the Svalbard community to kind of get involved in the activities and learn about the science that's still ongoing, but they continue to be important. And I think this webinar today shows you that bringing people together from around the world still remains a really important aspect of what we do. And our webinar series ranges in content from very specific applications such as radar systems, which is the one that I led last year, to kind of more broad research areas in terrestrial research and the environmental impact of research and so on. So the themes of the webinars are quite wide-ranging, so I'd keep on top of the webinars that we do have if there is anything that might be of interest to you. Every year now, we run an online conference. This began in 2020, again, kind of initiated by the conditions of the pandemic. And we use these conferences, again, to bring together people from the Earth observation community in Svalbard and promote work that people are doing, particularly promoting the works of PhD students, postdocs. But we also have researchers and more senior academics present as well. Yeah, and we provide awards for early career research, which, again, I think SIOS and the RSWG in particular is really helping to build this community for early career researchers. And we had the second online conference in 2021, similar ideas, but this time actually building collaborations with the EGU divisions, which I think is quite important moving forward for SIOS, and the RSWG is kind of building links to the other geoscience networks and Earth observation networks in Europe and around the world. Okay, so some of the tools that we're developing in the remote sensing working group kind of shown on here. So there are various tools on the SIOS website, such as acquisition plans for Sentinel data. There's the Sentinel Mosaic, which gives you information about the various data sets that have been generated from Sentinel data over the last 3 days, I think it is. And there's also a tool to look at comparing different products generated by Sentinel data over the location that you're specifically interested in. And of course, one of the key aims of the remote sensing working group is to patch up your field data. So we work with field scientists to understand their needs in terms of remote sensing data and understand how remote sensing can fill in the gaps left by field data, because of course, field data can't cover the whole of a location such as Svalbard. So we're currently in the process of mapping the needs of researchers and evaluating the possibilities to provide observations from remote sensing where there has been, especially in the last couple of years, less field campaigns. But I think this is going to be important going forward. I think building on the knowledge that we've gained through the pandemic. And if you are working in Svalbard, then we would love to hear from you and get your feedback on what you want and what you need from Earth observation data. So we currently have this user requirement survey out. I'm sure a link can be posted in the chat if you don't use QR codes. But we just want to know what kind of what stuff that you would want from us, from SIOS, in terms of Earth observation data and geospatial products, and what you would like to see us kind of work on in the next few years to help you in your research. And we're pretty active in outreach activities. We have on social media the image of the week, which shows very nice images of the Svalbard archipelago from satellite data and from pictures. Just keeping activity going through our social media channels and highlighting the kind of the excellent location that Svalbard is, because it's a pretty amazing place. To bring some of the science work together, we have a special issue out. The hard deadline, as Sridhar has put on this slide, is the 30th of June. So if you are interested in contributing to our special issue, then please do submit. Although I guess if you have decided to submit to this special issue, you probably have already decided. But again, it's just an opportunity to bring people's research together who work on Earth observation data in Svalbard, and it's quite a neat collection of science results, I think. And I guess we're kind of building towards the end and kind of building on this idea that early career scientists are really important for the progression of SIOS and the SIOS RSWG. So I was the first observer for the SIOS working group, and I've been active in Svalbard science the last few years anyway, but it's been really good to kind of be a part of the working group and to learn about how SIOS works in the international community. And over the last year, we've had Sarah Aparicio, who's also joined us. She's interested in melt ponds and sea ice, but she's brought a lot of new ideas to the SIOS RSWG. And if there are any early career scientists on this call, then maybe you are the next one to join the team. Hopefully we will have a call out relatively soon for the next observer to join the group. And it'd be great if you are interested in this, and if you have any questions, you can contact Sridhar or me as a current member of the working group. And just to finish off with some upcoming activities and ongoing activities. So we're building a unified platform for satellite data availability in Svalbard. This is something I'm working on, slightly delayed because of my finishing my PhD, but this is a platform which we're reviewing what data is available in different locations in Svalbard so that field researchers and geoscientists in general can understand what's available to them and whether there are ways of using it for their research. We're trying to build facilitate dialogue between field scientists and remote sensing experts, and that's ongoing. I think Sridhar is working on citizen science projects, especially for supporting Calvow activities. That's an ongoing project. And of course, you've seen the user requirement survey. And just to finish up on the opportunities, we have training courses every year, so watch out for those and the ECR Observer opportunities. There are regular calls for airborne campaigns in Svalbard. So if you are interested in those, watch out, because they're very useful and they have been very useful for a range of people. We have remote sensing tools, online conferences, webinars, and ways to patch up your field data with remote sensing. And I'm sure there's various things that we can do, and would love to hear more about what you think we could do to help you. And that's kind of where I'll finish up. If you have any questions, happy to answer them or pass them on to Sridhar, who might know more than me.